Basis path testing. In a software, whenever we are going to code, before that, we know how many paths we are going to traverse. So this basis path testing is a white box testing. Actually, it is a test case design technique, and this is proposed by Tom McCabe. So the basis path method, first of all, if you have written certain procedure or say made a flow chart or made a PDL, that is an algorithm, so the basis path method will derive the logical complexity measure of this procedure, of this procedural design, using this measure to define a basis set of execution paths, and they are nothing but the test cases. So these test cases which we are going to derive, this derived to exercise the basis set, these are guaranteed to execute every statement at least one, every path, every route at least one, whether it is if then else, loop, case. Flow graph notation. So we also call it as a program graph, and this is all to make or to derive test cases. So this flow graph is depicting the logical control. The control is, in any programming language, you are going to use if, while, do while, until, case, and the simple procedural statements. Instructions. So each structured construct has a corresponding flow graph symbol. That is, every symbol which you see here can be depicted as a graph symbol. So let us consider a procedural design representation. I am showing you a flow chart. Now this flow chart, we know the basis, whenever we started our computer science, we know how to make this flow chart. Now you just have to worry about these diamonds, because these are conditional statements, if else, because it can give you multiple paths. So in a flow chart, why not we convert it into more, say, understandable? And this is the flow graph. So we will be converting this flow chart into the corresponding flow graph. Well, we can use the flow chart also, but it is better that flow graph notation can be used, will be used, because you will see what we are going to do here. Every circle which you see here, they are called node, flow graph node, and they represent one or more procedural statements. Okay, I'll show you what is the difference between the flow chart and this graph, because a sequence of process boxes and a decision diamond can map into single node. There are arrows. These arrows are called edge or links, and they represent the flow of control, similar to what you see in the flow chart. Every edge, this is very important, every edge has to must terminate at a node, even if the node does not represent any procedural statement. Statement is simple instruction in the programming language, which you are going to convert. Okay. So let us say if else. So we start from here. If there will be one condition, if or the else condition. But I am saying we need to end it. So there has to be a node below. So an edge must terminate at a node. Okay. So we have while, do while, entry controlled, exit controlled. Sequence are some simple instruction, no condition, no compound. Now the area will be bounded by edges and nodes. These are called region. For example, this is a closed region. So all the closed region along with one region which is outside, the outside region. So we will be counting region, number of region which are closed. Along with this, we will be adding one more region which is outside. Now, whatever I just told you, let us convert this flow chart into actual flow graph notation, because actually we are going to compute the complexity cyclomatic complexity, and then we'll tell you how many test cases we can find out. Okay. So we started with this one. This is the first, yes or no. This is a conditional statement. Now, if this is a conditional statement, there are two paths. This is the first path. So where it is going 11. So we'll make a node 1 and we will terminate it into 11. First thing is done. Now coming to 2. 2 is in square box, so it is not condition, it is not even compound. So it is just an instruction. It can be addition, it can be a printf. We don't need it now. This is the difference between flow graph and this flowchart. We are only concerned about the diamonds. So 2 and 3 will combine. 2 and 3 will combine. And now 3, again, it will take you to yes or no condition, if or else condition. So 3 will take you to 4, 3 will take you to 6. So we have to have a node for 4, a node for 6. Okay. So let us combine this. But what do you see here? 4 and 5 are simple boxes. That is, there is just processing. There is no condition, no if else, no path or construct, logical construct. So 4 and 5 will combine. We'll make node. Now coming to 6. 6 is taking you, again 6 is a conditional statement. So it is taking you to 7 and 8. So we'll make a node for 6. We'll make a node for 7. We'll make a node for 8. Okay. So we'll make a node. I told you for if what we are going to do. So we have one node starting and ending in 2 node, and those 2 again ending in another node. So this is the final way. Okay. 7 and 8 you know. But you have to terminate it. It is going to go to 9. So you have to make a 9 also. So you have to end that edges also. Now coming to 10, because 9 is going to 10, 5 is also going to 10. So you have to make a 10 node and just join from 4, 5 to 10 and 9 to 10. Now 10 is again going back to going back before 1. Just take 10 and make an edge to 1. So I hope you got the idea how we converted a flow chart to a proper flow graph node. The rounds are known as, the circles are known as nodes. The lines, the arrows are the data flow, or you can say a flow graph. And these are the regions. The first region is this one. This is the closed region. Let me change the color. This is the another region because this is also closed. Let me make another region. One more region we can see. Okay. This is the third region. This is the third region. So 3 region. And this is not region, see, because this is outside. It is open. So all the open region will be counted as 1. It will be counted as 1. Okay. So we have 4 regions. Now sometimes what happens in the conditional statement are if, else, switch, while, do, while, all these are conditional statement. All these are if, while, until, case, these are conditional statement. But sometimes you have a compound statement with these conditional statement, for example, or, and, nor, and this will give you true or false. So a compound condition can be inside your conditional statement. So how do you make it? If you have a flow chart, you can make it. If you have an algorithm that may be written in some program design language, this can also be translated into a flow graph. How to convert it? See, this is if A or B. So a separate node is created for each of the conditions A and B in this statement if A or B. So this is a simple if condition, but inside this we have A or B. And A or B will give you result always true until A and B are false. So we'll start with A. We'll start with A. So if A or B, then procedure X. So A will give you, if A is true, it will give you X. The next line, then procedure X. So we make a node. As I said, a separate node is created for each of the conditions of A and B. Okay. So until both are false, you have to make conditions. So for A, if it is true, then procedure X. You don't have to worry about B. But since OR is with B, so now coming to B, you'll take the condition B now. Now B is true, again you will get an X. But if this is not, both are not true, what do you get? You'll go to Y. This is Y. And now I told you, you have to end it. You have to end it. So you have to combine this y and x with a node. And since x is also, you cannot leave x also, which is coming with a. So now combine x also with this node, and then you can follow the path, because there is end if. So each node that contains a condition is called a predicate node, and it is characterized by two or more edges originating from it. Any node from which two or more, or one or more, two or more edges are coming. Let me change my sentence. Two or more. It will be a predicate node. Independent program paths. So we made a flow graph from the flow chart. Now independent path is any path, any route that introduces at least one new set of processing statement or condition. In simple sentence, new edge has to be included. That is the independent path. Every independent path must include a new set of edge, this arrow. So independent path must move along at least one edge that has not been traversed. For example, let us find out what are the set of independent path for this flow graph. First one is 1. We start with 1 and then we came here 11. This is the easiest path. This is an independent path. What can be the second path? Let me change the color. What can be independent path? Because we are making set of independent paths. So we are going to 1, 2, 3, then 4, 5. Then you can go to 10, then 1, back again, and coming to 11. This is path number 2. This is once again an independent path. Now coming to the third path. 1, go to 2, 3, then 6, then 8, go to 9, 10, 1, and then 11. Now you are able to see that every time we are taking a new edge, every time a new edge is introduced. Let me show you one more path. Okay, I'm taking different color. Okay. So now path number 4. This is one of the set of independent path. We start with 1, go to 2, 3, go to 6, then 7, then 9, then 10, and 1, and then 11. Again, one of the edges included, new edge is included. But there are certain paths which are not independent path. Because if all these path 1 to 4 has been taken, I'll make one more path and you will be saying by yourself that no, this is not a path, because it is already including all the paths which we have already covered. So it is not a independent path. Okay, just see here, because this path, as we start with 1, 2, 3, 4, 5, 10, 1, 1, and then we go to again 2, 3, coming back. This can be a path. 6, 8, 9, 10, 1, and then 11. So this is not. Why? Because this is simply a combination of already specified path 1 to path 4, and does not traverse any new edges. So path 1 through 4, which we have devised here, constitute a basis set for the flow graph. This is the basis set. Set is a combination of number of multiple independent paths. I hope you got the idea. Basis set is not unique. If you and me are making the independent path, your path may be different, my path may be different. So different basis set can be derived from a given procedural design. Cyclomatic complexity. How many paths to look for? Whenever we are trying to find out the independent path from a flow graph, how many paths to look for? The answer is cyclomatic complexity. Cyclomatic complexity is nothing but it will give you the test cases. How many test cases? So every time when we take the independent path, it should include an edge or a control path which has never been touched, which has never been traversed. So it is a software metric, cyclomatic complexity. It is a software metric that, because we are going to get the number, that provides a quantitative measure, again getting a number, of the logical complexity of a program. This flow graph has been made from flowchart or a PDL, and this gives you the cyclomatic complexity. So cyclomatic complexity defines the number of independent paths on the basis set, providing you with the upper bound of the number of tests or test cases that must be conducted to ensure that all statements have been executed at least one. So cyclomatic complexity is all about giving you the number of test cases or the upper bound, how many paths you have to take. So cyclomatic complexity can be computed in three ways. You need to understand how to make this flow graph, then only you will be able to understand cyclomatic complexity. So let us see how many regions are there. Regions are all the closed circuit and one which is not closed, means outside. So how many you see here? R1, R2, R3 and one R4. These are the first thing, 4. Now cyclomatic complexity can be computed by E minus n plus 2. E is number of edges, n is number of nodes plus 2. Edges are simply the arrows, nodes are simply the circles. The third way to compute the cyclomatic complexity is just have to find out the predicate node. Predicate nodes are those nodes from where 2 or more edges are coming out, which are the predicate nodes. 2 or more edges are coming out. So you see the first node, 2 arrows are coming, so this is the predicate node. 2, 3, 2 are coming, predicate node. 6, predicate node. Actually these are the diamonds in the flow chart. So P plus 1, 3 plus 1. How many regions are there? 4. E minus n plus 2, this also will compute to 4. So the cyclomatic complexity of this example is 4. I'll just revise it. Cyclomatic complexity is number of flow regions, the 4 regions are there. So this is these number of edges minus nodes plus 2. So 11 edges are there, 9 nodes are there plus 2, this is 4. So now the third one, which is number of predicate nodes plus 1. So if you see these are, I'm just computing again the edges and nodes. So 11 edges, 9 nodes, and then predicate nodes are 3. 3 plus 1 is 4. So this all is giving you 4 value. So this 4 are the number of test cases. The value of this Vg is an upper bound for number of independent paths and number of tests that must be designed and executed to guarantee coverage of all program statements. This is cyclomatic complexity. Okay.